Alright class, today we are going to talk about some word problems with linear equations and a little bit of systems also, so let's get started. We have Luke and Bud go paddling on the Des Plaines River. They check out a boat, head along the river for a while, then turn around and come back to the boat dock. So I'm giving you some variables here. T is the number of minutes that have elapsed since they have left the boat dock. F of t is the function that they use to show how far they are from it on the way out. Then there's a different function for when they're coming back in. And they give you the two equations. F of t is 32t. Find f of 3 and f of 10. So basically they're saying how far away from the dock are they at t equals 3 minutes and t equals 10 minutes. So f of 3, you just plug a 3 in, so 32 times 3 is 96 meters. And if you do f of 10, you get 32 times 10, or 320 meters. Equation for coming back in is negative 17t plus 510. Find g of 18 and g of 23. So, g of 18, again, we're just plugging in 18 for t. And we get 204 meters. Now, this next one should be less because they're on their way in now. So g of 23, I'm not going to show the work for that. Plug a 23 in for the t, and you get 119 meters when you do the use the calculator. So all I did so far was figure out some points. I have the points 396 and 10 320 for the first line, and the second line I have 18 and 204 and 23 and 119. That's the second line. Now it says sketch the graphs on the same set of axes. So, use dotted lines for the graphs in parts of the domain where the equations do not apply. Alright, so what that means is when I'm graphing these lines, and let me do this as 5, 10, 15, 20, 25, and 30. And then we'll go up by 50s here. 50, 100, 150, 200, 250, 300, 350, 400. Okay, so I'm going to plot my graphs. First of all, we know that the initial starting point for the first line, I'll use the red for the first line, is here, 0, 0. And then we have the points 396, so that's about here. And we have the point 10 320, 200, 250, 320. Okay, so that's this line right here. I'm not going to graph the rest of the line yet. I'll show you why in a second. The other 2 points are 18 204. So about there, and 23 119. So 23 119 is about there, maybe a little higher actually. Okay, so if I drew this line, and again this is not exact, it's just how my graph looks. What happens is this line will meet with this line at about here. And what happens is this graph is a graph of them leaving the dock and then coming back. So it says graph the lines but use dash for where the domain does not apply. Well, once they hit this point, this line we're not going to use anymore because we're turning around and using the other equation. And same thing with this, we don't use this equation, we don't use that line for anything less than that intersection point. So the red line is them leaving the dock, and then they hit a place where these functions are the same, and then they start turning back and going back towards the dock. So that is my sketch. So calculate the point where the graphs intersect. Let's calculate this point. Well, you just set the two equations equal. 32t is equal to negative 17t plus 510. And when you solve this, add 17 over and divide by 49 for the 510. So you get 49t equals 510. You get t is equal to 10.408 minutes. Okay? And when you plug that back into one of the two equations, 10.408 times 32, you get about 333 meters is how far they went out. So, that tells us what is happening in the real world at the part D. Well, think about it again. The boat is leaving. Now it's on the new line coming back. The boat turned around. Okay? What was happening? And then at that point, they turned around 10 minutes and 10.408 minutes in and 333 meters out. When did they arrive back at the boat dock? Okay, so that means that we are on the blue line now, and we want to know not when t is 0, but when the distance is 0. So we're going to say 0 is equal to negative 17t plus 510. I want to know when the distance is back to 0 using this equation. And when you solve this, you get negative 510 equals negative 17t, and we get t is equal to 30 minutes. So actually my graph was pretty accurate when I graphed it. Okay, so they arrived, it took a whole journey of 30 minutes. Then it says, assuming that they're paddling at the same speed through the water for both parts of the trip, did they start out going upstream or downstream? In case you guys are wondering what that means, upstream means that they're going against the current. So even though they're paddling at the same rate, it'll take longer because they're going against the current, whereas downstream, they're paddling with the current, they'll be moving faster. Now, there's a few things you can do to justify your answer. First of all, just look at the graph. Which one did they start off going faster at? What was the faster slope? It looks like the beginning of the journey, they were moving faster. The other way you could do it is looking at the math. It took a total of 30 minutes to do the whole trip, right? But it took only 10.408 to do the first part. So that means the second part took 19.6 approximately minutes to come back, which means they started going downstream because the current was helping them. Because, like I said, they went 10 minutes downstream, about 19 minutes coming back. Try to figure out the current of the Des Plaines River. This is a little tricky. Pretty much, we have to use this D equals RT again, except for our rate is different. So for the leaving the shore, for going out, our D is equal to the rate plus the current, because it's faster, right? So our rate is actually going to be added to it, times T. And coming back in, our distance equals rate minus the current times T. Okay? So what happens here is we can plug in our information. We know that they both travel a distance of 333. We know the rate, or we know the time for each one. So I can plug in my information. 333 equals the time for going out is 10.4. And then R plus C. And then coming back in, it's 333, 19.6, because that's the time coming back in. And again, we travel the same amount of distance both times. So you multiply this out, and actually we don't even need to multiply it out. What I would do to make this a little easier is divide these numbers. So for example, this equation here, I would just divide by 10.4. This equation I divide by 19.6. So we get a new equation. We get this equation here. We get 32.019 is equal to R plus C, and I get 16.99 is equal to R minus C. Well, now we have a system of equations. And this is nice for elimination. If you guys can see that, the C's will cancel if I add down. So what I'm doing then is adding the two numbers together. So I get about 49.009 equals 2R. So the rate is equal to 24. 0.505. So, but that's not what I want to know. I want to know the current, not the rate of the boat. So I go back to one of these two equations. I'm going to pick this one here. And I say C plus 24.505 has to equal to 32.019. So my current speed is equal to 7.514 meters per minute. Okay? And again, all I did there was use D equals RT twice. Except for, again, our R is really the river plus the current, the river minus the current, depending on which way you're going. And then I just put the numbers in that I know, divided those out, and then did a system. And we got the current speed. Okay? Don't worry too much about that, but it's an interesting way to see how we can use systems to find pieces of information that we're missing. Alright. Terry wants to make 40 pounds of a mixture of nuts for her next math party, because we all know how awesome math parties are. Although 40 pounds of nuts is a lot. I don't know how many people are coming to this party, but she wants her mixture to include peanuts that sell for $2.40 per pound and cashews that sell for $3.20 a pound. Right now, I'm going to say X is equal to peanuts and Y is equal to cashews. I always make a chart for these, but you don't really have to do that. We can just go back to what we know for our system. We know that she can afford $2.70 per pound. That's what she wants, and she wants 40 pounds. So remember, when we do systems, I always talk about we want a equation that just talks about the amount of pounds or a quantity, and then we want an equation for cost. So the first equation we can come up with is we want the number of peanuts and the number of cashews to be 40 pounds. Okay? We also know, and this is where people make the mistake, so be careful. We know that peanuts sell for $2.40 plus cashews sell for $3.20. Now, here's where the mistake comes in. Most of you guys did this with the balloon one with the Mylar latex balloons, and it was fine. There was no problem there. When you're dealing with per pound, though, there can be a problem. She can afford $2.70 per pound. Do not put $2.70 here. That doesn't make any sense, because there's no way she could have a pound of peanuts then, right? This equation is saying the number of peanuts times 240 plus the number of cashews times 320 has to equal we want it to be a mix of $2.70, but again, there are 40 pounds that are happening here. So my actual equation becomes x plus y equals 40, and then 240x plus 320y equals $108. So that is what we will use now to solve our system. You can do it either way. You can decide to do it with what's it called? Substitution or elimination. I'm going to do elimination. I'm going to multiply this whole thing by negative 2.4. So I get negative 2.4x plus I should just say minus 2.4y equals 40 times 2.4 negative is negative 96. These cancel. You get positive 0.8y equals 12. Divide that by 0.8 and you get y is equal to 15. Alright, which means that x, if they have to add up to 40, to look back at the original equation, x has to be 25. So, that means that for this math party, Terry wants to mix it so that she has 25 pounds of peanuts and 15 pounds of cashews. And that is the final answer. Again, setup very similar to the other word problems we did, except for this piece here. You don't just equal it to the thing per pound. We want 40 pounds, so you have to multiply that by the 40. And then finally, Nathan and Russ went to Lenny's after their jazz concert last Friday night. They noticed the 2-egg breakfast with hash browns and toast cost $1.85, and the 1-egg breakfast with hash browns and toast cost $1.35. So here's the it says how much was Lenny's charging for each egg and for the hash browns and toast. don't be careful. This hash browns and toast is one thing, so we're going to call that y. Egg we'll call x. Okay, so don't get bogged down with there's three things happening. We do not have three variables here. X is our eggs, y is our hash browns and toast. So now, again, whenever we're doing these problems, guys, you could always pause the video real quick to see if you can set up the word problem first. So why don't you do that now, and then I'm going to set it up ourselves. So it says 2 egg breakfast, so 2 eggs plus the hash browns and toast equals $1.85. We also know the eggs, 1 egg and a hash brown and toast equals $1.35. So here's our setup. We just now have to solve this. You guys should be able to do that. Let's multiply this by -1. So we get negative x minus y equals negative 135. And we have this. So 2x minus an x is an x. These cancel. The y's cancel. I've used that already. And then 185 minus $1.35 is 50.50. Okay, that means that y, because x plus y, has to equal $1.35. So 0.50 plus y is equal to $1.35. So y is equal to 0.85. So that means that each egg is equal to 50 cents. And then the hash brown toast combo, that was awful right there. Hash brown and toast equals 85 cents when you order that combo. Okay? Again, it's all about reading the question and understanding what to do with it when you get it. Okay? I hope you guys understood. We'll go over this again tomorrow, and you guys will have some fun word problems to do in class. One of our favorite worksheets of the year.